Hi, everyone. My name's Diana Sinton. I'm here supporting this virtual consulting office for iGuide. We like to have our VCO sessions be able to provide information and stories, and often on technical topics. We're glad today to have Matt Turk with us from the UIUC School of Information Sciences. We're going to get started in just a couple of minutes. This session will be recorded, and after it's processing, it will be posted onto our VCO website. This is a regular Zoom meeting, and you have control over your own microphone. So we request that, for the sake of the speaker's anxiety, you don't unexpectedly turn your microphone on or off. But there will be time at the end for some Q&A. We'll wait just one more minute now till we get started, because I can see that there are still people actively joining. All right, let's get started. Again, we have Matt Turk here with us today from the School of Information Sciences at the University of Illinois at Urbana-Champaign. We're glad we're able to offer this topic on data storytelling as part of our iGuide VCO series. Scientific communication is an important hallmark of the activities that iGuide pursues and supports. So with that, Matt, I'll turn it over to you.
Thank you. And so I'm Matt. I also want to emphasize something that Diana said earlier before, I think maybe before some of you have joined, which is that this is, I'm happy for this to be as informal as you would like. And so if you have comments or anything like that, please either just interrupt me or use the hand raise, and I've got my dual screen set up, so I should be able to keep an eye on the chat as well. As Diana said, I'm from the School of Information Sciences at the University of Illinois. And one thing that I should mention is that my background is in astrophysics. So I originally got my degree by studying the formation of the first stars in the universe, which is a computational science problem in many ways that for decades was out of the reach of telescopes. And so I spent a lot of my time trying to understand what simulations were telling us and how we can understand that in the context of the real world around us. There's a possibility toward the end that we'll have time for a demonstration. If we do so, I will utilize Blender to do that. And so if you want to follow along with Blender, if we happen to have time, and as the time is progressing, I'm starting to think we probably won't, but if we do, and you want to follow along, please go ahead and download it. You can either get it from blender.org, or if you use Steam, which is a popular service for playing video games and installing software, you can also get Blender directly from Steam. So let me start out by saying that a lot of what we think about when we think about data storytelling is all about the connections between different people and the connections between different communities. And so when we design a visualization, and that's really what we want to do, when we design a visualization for our community, we want to build on what we know about our community. We want to understand the way that they'll be coming to a piece of information, whether the position that they arise from is from the layman's perspective, or if they're an expert in a field, or if they're somewhere in between. And we want to ask a variety of questions about what it is that we know about them. We want to ask ourselves, what do they know about the situation? What do they know about the scientific background? What do they know about the context that they're being presented things? What conventions will those people assume about the way that information is presented? And I'll return to that one in just a moment. But we also want to ask, are the people that we're presenting to able to fill in blanks of information? How much of the story needs to be told? I was watching a television program not that long ago where there was this beautiful sequence where there was, one character talking to another, and we were left to infer a number of things about one character's background just based on the facial expressions and so on. But we were allowed to tell that story to ourselves, and that's something that we also have to ask about scientific visualization and data storytelling. So I'm going to start with a quick little quiz, and what I want you to do and let's see if there's a way. There's probably not a way that we can do this unless I enable polls, but I don't think polls are always available. I want to ask you a quiz. You walk into an unfamiliar sink. Okay, and this could be in a restroom, it could be in a kitchen, it could be at a hotel, it could be anywhere. You walk up to an unfamiliar sink and you need to wash your hands. And I want to ask you, how do you know which faucet or which knob or what is hot and which one is cold? So go ahead and either speak up or answer in the chat. How do you make that decision? How do you know which is hot and which is cold? Left tends to be hot. Right is cold. Left hot if there's no sign. Convention that left is hot. Blue is cold and red is hot. A label, look for any colors on the taps, red versus blue. These are all great answers, and they mirror exactly what I would say. And in fact, when we bought our house, we had an inspector. They always do these house inspections, and one of the things that came up was that there were we have two showers, and both of them had the taps reversed, and this was marked as something. So to the left was cold instead of to the right, and that was a big problem. They showed up in the house inspection. But this is basically a very common thing, right? We all sort of assume that blue is cold, red is hot, left is cold, right is hot. I'm sorry, left is hot, right is cold. But the thing is that this depends on our understanding of the situation, and it also depends on our context. Because what if we were to talk about, say, I mentioned that I come from an astronomy background. What if we were to instead ask if you saw two different stars, or if you saw a stove, which would be hotter, blue or red? Well, it turns out that when you're using black body radiation for your source, blue is actually hotter and red is colder. And we bring these different contexts to our different situations, and they inform the way that we understand things. There are consistent visual languages that people utilize in different fields. So I want to talk a little bit about building on this notion of this relationship that we have with reality, with data, and so on. I want to talk about something that my friend and colleague Kate McDowell calls the storytelling triangle. And the storytelling triangle is made up of three different components inside a set of relationships. And now the first component is that of the storyteller, the person that is the person or the entity that is telling the story, that is somehow interpreting information and then transmitting that information to you. The second component in this triangle is that of the tale. It's the notion that there is some platonic truth out there that is being interpreted somehow. There is a concept or a piece of information that is being transmitted. And then the final component in this triangle, the perhaps most personal component for the people that are viewing it, is that of the audience, the person or the people that are receiving the information. And with these three components, we have not just these three individual components, but the interrelationships between those three. So there is a relationship that is constructed between the teller and the tale. There is some interpretation that is being applied or understanding. And then the teller transmits that information to the person that is receiving it. So there's data, we're interpreting the data, and then we express that information. And then that allows a relationship to be constructed between the person that receives the data and this underlying concept. So if I'm conversing with you, you're telling me a story, I then construct my own understanding of what occurred, of what the truth behind that original story is. And now those three relationships are as distinct and independent as the three different components that went into them. And this is really key to understand. In some ways, this is a different framing of the way that information is transmitted, between the receiver and the noise that gets added in between, and so on. But it's also really important to be able to take these three different relationships and proactively deconstruct them in order to better construct the visualizations. So if we, I guess, let me back up for a second. It's important to specifically address these three different components and these three different relationships in order to tell the best story that we possibly can. Now we can think about this as also three different categories of visualization as well, because there are different types of category, different ways that we construct visualizations for different audiences. And there are basically three different types of relationships that exist. There's the visualizations that we construct for ourselves, where we're really targeting ourselves as both the teller and the told, where we are building out visualizations that allow us to deepen our understanding. And these types of visualizations, particularly in scientific visualization, often make different assumptions and exceptions for constructing information transmission. There are also the visualizations that we make for our peers, where we really do focus on constructing as much of a representation of the underlying data as we can. We want to be able to construct something so that others can answer their own questions about it. And then finally, and this is something where, in work that I've done with, or that the Advanced Visualization Lab has done, that I've been honored to collaborate with them on, we really focus, are the visualizations that we make for everyone else, where we really focus on that relationship with the audience, where the audience is somehow the most distinct and the most removed from these different situations. Each one of these presents different opportunities. They have different needs for narrative, for interactivity, for control, and they also have different needs and opportunities for utilizing different visual languages. I have a very specific thing in mind for this. Specifically, when I am constructing visualizations for myself, when I'm constructing visualizations for my peers, I know innately the visual language that perhaps they will expect. I understand the way that they may be thinking, the questions that they might answer. And I also understand the way that I can communicate information to them, because I'm very akin to them in their current situation. So let's ask two questions before we go any further. And we're going to use these two questions to really center ourselves in this concept of how do we construct stories of our data. We want to ask ourselves, what do we want from visualization? So what is it that we want to accomplish by taking data and, instead of, say, reading it to someone, turning it into a visualization or turning it into a sonification or a physicalization? What do we want from being able to do that? And why do we do it? And the two questions are different, even though they appear very similar. Why do we visualize? There are a lot of different reasons that we visualize data. In many ways, they turn into different forms of saying that we want to tell a story, but there's also an artistic expression to them that we shouldn't deny. So let's say, what do we want from visualization? Very commonly, we answer things like, we want to inform people. So we want to tell someone something very specific. Or we want to share knowledge. We want to be able to share an understanding. We want to be able to share a broad sense. We want to share very specific pieces of knowledge or information. We may want to empower people to make better decisions. And this is something that is particularly key for iGuide. Many of the different visualizations and scientific projects that I've seen at iGuide have been very focused on empowering better decision making. And there are different ways that we can empower decision making. One of them, of course, is by giving better information. But giving better information and giving more focused information are often conflated, and they don't always have the same needs. And then finally, with visualizations, we also often want to share a feeling. And this is something that sounds softer. It sounds a little bit more removed from some of the things that we are typically dealing with scientific data visualization, but it is something that is really important to keep in mind. These feelings might be awe, they might be things like sadness, they might be pride, they might be joy, it might be excitement, but there are feelings that come with our data visualizations. Why do we visualize? And so, again, I want to emphasize that answering this question and really thinking through our motivations for doing these things allows us to better formulate the stories that we want to tell with our data. We visualize in order to tell people stories or to tell stories to ourselves. We visualize in order to understand cause and effect. We want to visualize in order to understand different levels of detail. We visualize because we want to understand the way that things change over time. We visualize in order to tell stories to people in our communities, whether those communities are our local communities, our scientific communities, our communities of peers and colleagues and friends, or whether those communities are virtual communities that are joined by whatever type of connection we may have for us. And finally, we want to visualize our data in order to tell stories to everyone. We want to have people to be able to, we want to enable individuals to take data and relate it to themselves and their lives in a way that resonates with them. And stories are really important. They're how we communicate not only with others, but with ourselves. We tell ourselves the stories of, my day. My day today was terrible because of, events X, Y, and Z. Or these are the different things that I've noticed over time, and then this is the story that evolves out of them. It's been a rough couple days for air quality in Champaign, and so, this is the story that I'm telling myself about that. They're also how we organize information, how we interpret information, and how we relay that information. And importantly, stories are embedded in how we interpret the world, even at the smallest scales. So I'm going to show you something in the next slide that is a story. And there are aspects of this story that I want to emphasize and bring up to you. And then I'm going to give you an opportunity to tell me a little bit your thoughts on it. So I'm going to show the story. And I want you to tell me what are the aspects of the story that immediately resonate with you. Okay, the story started over. I don't see any typing in the chat, but that's okay. I want to bring up a couple things. Everything is a story, right? And cinematic opportunity. Yes, very nice. What I want to bring up here is that there is some sort, Nicole, excellent. Yes, there is some sort of goal or objective for this guy. And so let's break this down for a second. We see our protagonist enter the screen and then progress left to right. I want to ask you, left to right, is that a progression that you are familiar with? It about 25 years ago, there was a column in Roger Ebert's column where he wrote about the cinematic language of progression, of motion, of moving from the left-hand side to the right-hand side, and how in cinema, it turns out this is a nigh universal phenomenon, even in cinema, from right to left languages. And this was fascinating to me because it means that there is this fundamental progression that we see even in things like our Cartesian axes, in our movies, in our video games, that we move left to right. And it seems to, whether by some underlying characteristic or whether through cultural diffusion, it seems to be independent of the way that, say, our languages are written. And so when we see things that invert this story, it brings with it a different feeling or connection. So for instance, when we look at something like this, this is from a movie that came out in 2017, 2016, called The Last Jedi. It's an homage to a Japanese film, Ran, by Kurosawa, where we see progression from right to left. It's immediately not disorienting, but it's immediately different. And that distinction is important. And so we can rely on these different stories, these different conventions and frameworks in order to communicate information about progression, about change, and so on and so forth. I'll give an example that oftentimes in astrophysical data, we utilize redshift as a progression. But the thing is that redshift goes from 0 to high numbers, and the high numbers are long, long ago. And so it's very common for the left-hand side of a plot to be the current time and the right-hand side to be far, far ago. And this doesn't really mesh well with our understanding of the way that progression works. And so every time we make a decision to follow a convention, it's just as important as when we make a decision to deliberately invert or subvert or challenge that. And this brings me to the next point, which is that whenever we are visualizing data, whenever we are telling a story, fundamentally, we have to be lying. Oh, Paul has a statement. I'll read it here for the video later. With respect to the study of shapes in a geometric modeling seminar, coordinate systems were dismissed by one professor as a requirement for geomatics use cases only. I will confess that I think there's a lot to unpack there that I don't immediately understand. And I suspect that that it speaks to something more profound than what I was getting at. I do mention the expectation of coordinates. You're right. So it's entirely possible that this is more complicated, but much like we tell lies to visualize, I suppose we can think of my statement as a form of also simplifying for the purposes of this. I have the pleasure to work with Stuart Levy, and he said at a conference that I was at about 20 years ago that we tell lies to visualize. And I didn't understand what he meant at that time, but I have since come to understand that that really, yes, this is extremely key. Visualization is a form of lying. When we take data and we represent it, we are saying this thing, which is a particular thing, can be experienced another way. But fundamentally, it has to be a reductive operation in order to transform one item into a visual representation. There is no possible way that all measurements, that all systems, that all visual representations of those measurements can fully encompass the data that went into them. I may be able to be represented as, say, a member of the passenger manifest of the Titanic, right? Or someone may be represented as on the passenger manifest of the Titanic, and we may say visualizations of how different people survived as a function of their economic income and so on. But none of those things include the various different hopes and dreams that those individuals had. There is a fundamental reductionism that we have to apply. And so we have to strategically represent one thing as another thing. We have to strategically make a decision. We decide one piece of data can be represented somehow visually. And then on top of that, we make another decision. We'll show it from this angle. We make another decision. We show it from this color as this color. We make another decision. And each subsequent decision takes us further and further away from that original thing. We have a concept of someone's life or biography, and then we turn that into a movie or a book. And consistently, we are making decisions about what is important to the story we are choosing to tell, what is not, and how we can then represent those. So here is a simulation or a visualization of the formation of the first galaxies in the universe. This was conducted based on a simulation conducted, I believe, on blue waters at the University of Illinois years ago. And what it is it's a visualization that shows the different ways that individual protogalaxies are lighting up, emitting radiation or light, and the way that they then ionize their their surrounding regions and put that light out into the universe, turning it ultimately transparent. This visualization is breathtaking in the amount of information that it conveys, both in the specifics of the way that individual clouds are structured and the information we could get out about their topology and the way that they look, as well as the general overall feeling that this is a system, a universe in which things happened at some specific rate with some specific distribution, and the way that it would feel to walk through that, or the way that it would feel to fly through that. Let me make sure that I'm on my highest quality. I guess I am. And then additionally, I'm going to back up for just a second here. We can choose at various different times to show different levels of information. So throughout this entire visualization, we are telling the story of the universe, but we also find a way, oh, absolutely. We also find a way to elaborate on the information about the way that the simulation was conducted. So yes, I'll talk about the topology here. So basically, the way that these we expect the universe has worked is that in the early stages there were lots and lots of electrons that were separated from their atoms. So we've got fully ionized universe. Then there was a period of recombination about 300,000 years after the Big Bang, during which it was optically thick to visible light. And then after galaxies started lighting up, basically what would happen is there would be ionizing electromagnetic radiation. And then the way that it would break out, and you can see that here, the way that these stars forming here would ionize their regions was highly dependent on the structure and shape of the filaments and the dark matter. I'm sorry, not dark matter, but and the baryonic matter that surrounded them. So the densities and so on. And so understanding the topology of these ionization fronts. And so the notion that you've got individual bubbles that are growing that don't necessarily go strictly one over r, or that don't go with fixed radii, but radii that change based on recombination rates and whatnot, and then ultimately form a web that ultimately form a fully ionized universe that is optically thin to optical light is an interesting question that we can say things then about the observations that we have of the universe at these early times. So the topology here is it's a combination of things. It's the topology of the way that the clumps form in the early universe, and where they form, and that's a combination of collisionless and collisional matter, as well as the topology of the way that the ionization fronts expand. And you can see that here, these ionization fronts don't expand, strictly speaking, along smooth spheres. They expand along, funny shapes, sometimes like butterflies even, and so on and so forth. But this is a visualization where we had a very specific story that we wanted to tell. We wanted to tell a story about the way that these protogalaxies lit up the universe. And in doing so, that they polluted their environment with these heavier elements. And as soon as those heavier elements got out there, all of a sudden, the entire structure of the way that ionization bubbles formed changes, because the character of star formation changes. And then as we move on, we can see we can also tell stories using similar visual language, but not identical, of the way that our galaxy, the Milky Way, has evolved. And so this is a simulation of a Milky Way-like galaxy, and the way that it evolves. And each one of these is an ionization bubble, and every so often you'll see a supernova go off and change its surrounding environments. But we're utilizing similar, but not identical, visual language here. We're making the same reductionist operations in the way that we are presenting the data. And so we're leveraging our familiarity with a given story here in this situation. They are different time frames. So this one is over, I want to say, about 1 billion years over the entire course of the simulation. I might be wrong on that, but somewhere in that order of magnitude. And the other one is probably let me think about this, because the individual ionization fronts are going to expand reasonably quickly. And I think that one, I should check before I say anything. So I would say they're probably within an order of magnitude of each other. But the first one, things change much more rapidly in character and structure, whereas you see that in this one in particular, they've largely been about the same. But that's also something that I should mention, is that the way that we bring time into these is something that can be a little bit confusing. And you know what? Just for fun, let me real quick. I want to do something here. I don't. I don't think you can see this just yet, but I will. I will pull it up. No, you know what? No, sorry. Let me go back. I will show that at the end. But the question of time is a really tricky one to address, because in particular with some physical phenomenon, what we found that the time frames vary so wildly over the different regions of interest that it can be very difficult to really orient the viewer and to let the viewer know where they are in time and space. Another thing that we've struggled with, or not struggled with, but that we've had to address, is that oftentimes there's a bit of a degeneracy in when you're looking at things changing over spatial scales and over time scales, and trying to navigate that can be tricky. So if we return to our concept of the different types of groups that you are visualizing for, we can think about visualization for yourself as telling a story to yourself where you don't actually know what's going to happen. You can take shortcuts. So, you're just pulling something up in CartoPy, or you're just pulling something up in MATLAB or something like that. You'll probably skip labeling things, colors, so on, and maybe not exclusively, but sort of. And then you just got to make sure that you're not lying to yourself. So you typically explore data by changing how you visualize it based on its different characteristics. You know a little bit about what information you have that would be visually interesting. You know a little bit about what you don't have in order to understand the importance of data. And let me, in the interest of time, move on a little bit and say that one of the biggest tricks and challenges that we have when we are constructing scientific visualizations that start out with visualizations that we construct for ourselves is that there tends to be a curve in the amount of efforts and the quality of our outgoing visualizations. And one of the things that we see is not that when we construct really high quality visualizations, that immediately at low effort we see a change in the quality of the visualizations, but rather that what we want to do is we want to get to a higher quality visualization, but there always tends to be a maximum amount. And that's something I want you to keep in mind. No matter how polished something is, there's always going to be a point of diminishing returns. So when you're designing a visualization for your community, so moving on from the visualization for yourself, you can build on what you know about them, what they know, what conventions, and we already talked about that a little bit. But this comes down to a notion of a vocabulary of data analysis. So figuring out the way that data resides and how people think about it. And when we construct stories, we often think about the way that data can be turned into a story as falling under one of several different operations. There's the registration of data. So taking data and saying this data corresponds to this time or this place. There's the transformation of a given set of data. So taking data and saying that we may have this information, but with that information, we can also construct these other pieces of information. There's a sub-selection of data. So taking data and then turning that data into a smaller set of it. So for instance, you may have a full data set that tracks any number of different variables, or in a simulation may have a number of different pieces of information that are carried along with it. And not all of those are necessary to a final visualization, either by their region, their spatial location, or by their character. And then finally, there's some reductionary operation. So as an example, the two visualizations that I showed actually had large-scale reductions applied to them. And those reductions were rays passing through them. It was the process of taking individual pixels and then casting out through them from a camera and imagining what information they accumulate along the way. So reducing a three-dimensional data set into a two-dimensional pixel array. And when we think about registration, and when we think about this in the context of data visualization, oftentimes what this means is taking data that is laid out on a disk or laid out in some sort of conceptual framework, and then turning that into something that has different connections passed throughout it, that is structured in some way, that has characteristics, whether that be spatial or physical or not, and then taking that information and then turning that into something that is corresponds to something in the physical world. And in essence, what we do when we do that is we take a set of one or more data sets and we construct an f of x. And that f of x is essentially saying we know how to turn a position into one or more pieces of information. We know how, given our data set, to say this is what a value is at a given point. So in the room that I'm sitting in, for instance, my f of x might be some closure function that says at this vector, what is the particulate concentration of dust, or what is the micro velocity in the air at this point, or what is the temperature of this given gas parcel. What is the function that I can use to query that? And if you look at a map, for instance, this spatial representation, the f of x is how we then turn a given set of sensors for air quality or for temperature or humidity into a map of a given region. Registration also is not always limited to situations like having finite volumes or things like that, where it's all nicely, clearly laid out, but also can be things like having a fixed set of data points where you have queries, and then turning those queries into some sort of representation, and then applying a sampling function where you have some sort of a closure that perhaps queries the nearest neighbors, or integrates over a given set of nearby values in order to once again construct some kind of a closure function. And of course, in the limiting case, this can be a closure function that's defined by a delta function, where you only have information at any given specific point. And then, of course, there are transformations that we apply to our underlying data. One of the most common ways that I think about this is, good question. Oh, that's a private message. I was asked, have I used Gaussian particle approximation GPA for the visualizations? We've used things like smooth particle hydrodynamics, but we've also used Gaussian splatting. But I suspect that Gaussian splatting may mean something different in modern AI contexts to what we've used in the past, which was a much simpler process. And I'll talk about that more afterwards. Transformations are things like taking primitive variables that exist, say, in your observations or on disk, and then combining them. So for instance, I might have a simulation, or I might have a calculation or an observation where I have x and y velocities at given fixed spatial locations. Of course, if I have X and Y velocities at given spatial locations, I know how to turn those into a total velocity simply by adding them in quadrature. Um, uh, so taking vx squared plus vy squared and the square root of that sum gives me the absolute magnitude of the velocity, and that's something that we can apply through a transformation. So this notion of having different primitive variables that fundamentally describe a system, and then on top of that having a vocabulary of derived variables. One common use case for this in visualization, particularly with volume rendering, is that you can utilize things like the gradient or the gradient of a curve, or the gradient as defined universe at fully local points across the entire simulation in order to identify surfaces and apply specular lighting as an example. And so being able to utilize these concepts is really key. And of course, selection can be things like filtering based on connectivity, spatial organization criteria. And we use this once again to tell stories by choosing what not to describe. Perhaps we're only looking in one particular area, and we only want to see those individual regions. Or perhaps we're defining our area based on different characteristics, and then we construct our visualizations on those. And then, of course, our reduction operations. So one example of this might be we have a particle that flows through something and we want to tell the story of that particle. Perhaps we have a probe that has been released into the ocean, and we want to tell the story of how that probe encounters different salinity areas, or how that probe undergoes different pressure regions and so on. And so we want to be able to tell a story along an axis or a path, or even some non-trivial manifold of information. So being able to query our data along these different things is as important. Now, this is a special case of what we saw with our volume rendering. With volume rendering, what we tend to do is we tend to integrate rays through an entire domain and then accumulate information along that. Right now, we're working on a project with black holes where we are accumulating information along rays that have been distorted by the change in the geodesic near to a black hole. And then ultimately, when we construct stories out of our data, we are progressing through a set of composability operations where simultaneously we start with one item and we move to another very deliberately and clearly. So we start with our data and just a bunch of line noise on disk. And then by registering that data in some sort of a fixed spatial plane or varying spatial reference frame, we can construct a representation of that. And then on top of that, we can apply transformations in order to identify, say, regions of interest. And then on top of those regions of interest, we tell a story about each one of them. So we compute, say, the masses inside a given region. And then finally, from that, we take our information, we transform it, we re-register it in a non-spatial organization in order to tell a story about the mass function of a given cosmological simulation, for example. And this is how we tell stories to ourselves, how we conduct our data analysis, and how we identify these things through a progressive set of operations of saying this means this, transforming information, applying reductions, and then composing these operations. But the thing is that our communities are not the only people that deserve to hear our stories. The group that I work in specializes in cinematic scientific visualization, which is designed to bring the techniques used for films and movies to data, to really leverage this notion of storytelling for everyone. And in this process, what we tend to do is we tend to evaluate our ability to tell a story by asking what lies can we tell? What can we say about our data? And I want to be clear, I'm using the word lie here in order to be a little bit edgy, but of course, I'll break down what this process really means because it's not properly lying. But what lies can we tell about the data? What truths must we tell about the data? And what is the story that the data is telling us, and what story do we tell the audience? And finally, we want to evaluate if we succeed. So throughout all of this, we think about things in terms of our stories, and we can roughly map our stories onto a narratology that gets used in studies of storytelling, in folklore and so on, where we have character, we have a setting, and we have plot. And as researchers, we map our data onto these narrative elements, and we must also take into our account our role in the presentation. So we have unique motivations, style, and methods in our storytelling when we construct a story for our peers or for our public, and we can codify this. But to do so, we have to ask ourselves, why are we telling a story? What is our motivation for presenting this information? There are many different motivations for presenting information, and they are not always necessarily advertised in the text. You may find that the three types of stories we have described map to one or more of these categories more frequently than others. So, what are some reasons and contexts you might anticipate for telling a data story? Who might be in your audience? Are they friendly? Are they ambivalent? Are they antagonistic? What is your relationship with them? Do you have a pre-existing relationship? Do you have any reason to believe that you need to be more persuasive or convincing than you would otherwise? And what do you want to get out? Do you want to lead your audience to a conclusion? So, for instance, there may be some instances in which your primary motivation is to persuade someone of a particular piece of information, or you may want to tell a story in order to communicate that something is important, that something is changing, that something needs to be dealt with. And there are different levels of communication or conclusion that you want people to reach in a research setting. So, for instance, you might want to engage in collaborative thinking with someone. Perhaps your motivation telling a story is to develop a collaborative discussion, to present something as an unknown. I may show you something and say, I don't totally understand why this is the way that it is. Or I may present something to you and say that I do know why this is, and you should believe me. There are also situations where maybe you want it to seem like you're collaborating, but you're leading someone to a conclusion. And how might you structure your talk, your tale, and choose what you do and do not include? But there are also times when you tell a tale just to tell it, to provide voice to information, to say, this is what we learned. And we don't know necessarily why this is critical. We know why it's important, but we don't know what decisions it needs to influence. And sometimes we tell a tale without knowing why, and then we discover later. You also have to ask yourself how you are telling the story. If there is a single piece of information, a state in between transitions like slides, narratives, you can think of how you navigate between those as falling into a few different categories. When you're telling a data story, when you're constructing one, there are a few different different ways, and this is not a full ontology of navigation, but there are a few methods. You can tell a story that utilizes narrative progression. Typically, you would then identify a variable, whether that variable is time or space, and you would move along that variable. Or perhaps that variable is investment, and you show how changes tend to reflect a greater degree of investment, how after putting this much time or effort into something, some metric changes. Or you might say this is what changes over time. And those two are not always the same, but they are often related. And you move along that variable where the narrative is keyed to an independent variable. It's not always time. There may be others. Do you always move monotonically? Do you move at a fixed rate? And this gets back to the question that was posed by Babs Buttonfield in the chat of what is the time frame? Are we moving monotonically? Do you move at a fixed rate? Do all of our tales and visualizations? How do we ensure adequate information coverage? How do we ensure that we aren't filtering out things that happen below the scale of our representation? Another way to tell a story is through an expansion of components. So maybe not presenting all of the information in narrative, but selectively expanding on individual components in order to show them. You might choose individual items, zoom in on them, describe them in detail. And you see this often with maps, right? You see things at a large scale, then you see things at a small scale. You see things where you expand on components in order to describe increasing complexity. And then, of course, there's also, when you present some stories, there's a nonlinear exploration. There's your ability to shift along many different variables, many different directions, or perhaps the variables are not as well defined. You allow full exploration on the part of the individual. Um, yes. Um, Here we have to ask yourself, what do you visit first? Are you visiting an informational node in a given context, and so on? You also have to ask yourself how controlling of the narrative process are you? Many of the cinematic scientific visualizations that we build are in fact fully controlled. There is a particular viewpoint that we take. There's often a narration, and you can think of this as similar to the way that films are constructed as well. Are you, as an auteur, personally influencing not only the presentation but the journey for the audience? Are you allowing them to have complete freedom of exploration? How restrictive are you, and where does the technology limit you? How reliant on appeals to emotion, empathy, relatedness, intuition is your data story? And so I'm going to wrap up by sharing a couple tenets of visualization and data storytelling. And the first one that I want to share is that visualizing data is not a strict subset of making an image. Visualizing data includes things like the collection of the data and the way that you collect that, the organization of the data, the representation of the data as well. And this is really just a tenet that is meant to indicate to you that if you think about visualizing data as just putting pixels on a page, that is a reductive approach that removes from your consideration the fact that you have to think carefully about the collection, organization, and representation of the data. The second tenet, and this is the one that I really want you to take away from this, is that we have to tell lies to visualize. It's a reductive operation, and the sin of omission, the lie of omission, is one that is unavoidable. But in doing so, we have to retain our fundamental honesty. And this is the most important thing in my book. We have to be honest when we represent things. No representation can completely convey the complexity of a data set. It's impossible because data sets cannot completely convey the complexity of the underlying phenomena. But some representations are better than others, and we can evaluate those representations. Our choices, when we make choices about visualizing data, have to be deliberate. We have to deliberately make a choice when we represent data. This is how I am choosing to represent it. And those choices must also be informed. They must be backed up by our understanding of the data. We cannot make these choices blindly. We cannot make them in the dark. We have to be backing them up with our data. And to do so, we have to motivate them. So that means not only do we have to be informed about the full context of our data as best we can and know that we are making choices, but our choices have to be motivated by that information. And then finally, our choices when we visualize data have to be justifiable. I have to be able to tell you why I chose to cut the color bar at a particular value. I have to be able to tell you why I chose to avoid showing, detail above a given resolution, and all of those subsequent progressions of choice, motivation, and so on have to be interrelated. We have to know we are making choices that are informed and motivated, and then we have to be able to justify those choices when we make visualizations. And so I want to end just by saying that, where are we now? So much of the work that we do in visualization of data, so much of the work that you do with your research is predicated on a simple concept that I don't think we can step aside from, which is that what is real matters. And so it is 11:54 and 32 seconds, and I'm going to leave it here. I want to say thank you for this opportunity to talk. Let me see if I can skip to my, I guess my export did not include my thank you slide. So let me just say thank you very much for giving me this opportunity. I hope that this has given you some food for thought. What is real matters, and the way that we choose our visualizations. If we stick to our concepts of honesty and understanding of our audience, I think that we can really make change in the world. So thank you very much. Okay, if anybody has any questions, I'm more than happy to answer them or fail to answer them in an entertaining way.
Thanks very much, Matt. I have a question, but I see that Xiaowen has also turned on his camera. So Xiaowen.
Well, I just want to say thanks so much, Matt. That was fantastic. Really appreciate your insights, and you also told your story along the way. I think that's quite a piece of power you rendered throughout the presentation through your own experience. Thanks, Dana. I thought that you would be the best to ask the first question, but since you put me on the spot, I'll do it anyway. So the question I asked is not something you touched much in your talk, but rather about the emergence of generative AI
Mhm.
in terms of creating visualizations and assisting storytelling. So I was wondering whether you could elaborate or say a little bit along those lines, how generative AI is changing the way we create visualizations and stories to assist us for the kind of amazing impact you were alluded to in terms of how do we do this in the right way, and how do you feel this AI change is coming for improving our work or maybe also disrupting our work? Thank you.
That's a great question. So I will say that I'm of two minds on it, right? There's absolutely an opportunity for utilizing generative AI to either augment scientific visualizations or in some cases give some sort of voice, if you will, to things that we aren't able to represent. I would say that there are, I'll give an example. We recently were working on a project that required us to convey sort of the magnitude of turbulence in the outer areas of the sun, and we have models for that that don't necessarily work with the way that we're the time scales and the size scales and so on that we're trying to tell, but that can inform things. And so we experimented with, and we ended up not using it yet. If it's still undecided if we will or not, using that to augment our visualizations, to provide detail, to do the enhance, if you will, at the corona of the sun. And what it did for me was it allowed me to try to explore in my own understanding how much of what we're trying to do could be applied utilizing, say, simpler technologies as opposed to more complex generative AI. And it also allowed me to ask what were the inputs to this generative AI that we would expect it to be able to produce higher level results. And it did look cool, but I also then wasn't able to compare it to to something else. At the same time, I was able to answer those questions. It was deliberate, my choice, to use that. It was informed by a lack of data in one area and a prevalence of data in another. It was motivated in the sense that I particularly wanted to show something that, were it not to be true in its specifics, were I not able to get the underlying data back out, I could still, that it still tells the same story. It just does so by conveying feelings in a different way. And I felt I could justify it. And so I was able to, in that particular instance, convince myself that utilizing generative AI can help to convey feelings without distracting from the underlying scientific information. And I think that's going to be the key question. Where can we use generative AI to augment without obfuscating or subverting the information conveyance. And I think it's going to be tricky, but it is frameable in that way. And I think that doing so provides opportunity rather than constraining us.
Thanks, Matt. Really appreciate your thoughts.
Okay, anyone else from the audience want to have one final question for Matt? Otherwise, we are at the top of the hour. And Matt, I really thank you for sharing these ideas with us. As you know, scientific communication is very important for the work that iGuide does. And we're really glad that we're able to work with the Advanced Visualization Lab in collaborative efforts.
Thank you very much for giving this opportunity. And please feel free to reach out, folks, at any time. I'm delighted to chat more.
All right. Thanks very much, everyone. This has been recorded. Once it is processed, we'll have it up on our VCO website. Check out that webpage and you'll be able to see all of our other upcoming scheduled activities, and more are being added all the time.